This is part 17 of the series Applications of Differentiation. In this optimization problem, we have two posts, one 12 feet high and the other 28 feet high, and they stand 30 feet apart. They're to be stabilized by two wires attached to a single stake running from the ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So here's a visualization of the situation. The 28-foot post, the 12-foot post, they're 30 feet apart, and the stake is somewhere in between them. So to be able to find an expression for the length, the total length of the wire, we are going to obviously use the Pythagorean theorem, because we're going to have this length of wire, which is the hypotenuse of this big triangle, and this length of wire, which is the hypotenuse of the smaller triangle. Before we do that, we're going to have some expressions for this bottom leg of both triangles. So let's go ahead and call this piece x. And since this whole thing is 30 and this is x, we're going to call this 30 minus x. Let's call this a, and let's call this length b. So we need to have an expression for a and for b, and our total length, we'll call that distance, and that's going to be a plus b. So let's start our work by trying to find an expression for a. So this is going to be 28 squared plus 30 minus x squared. And b is going to be x squared plus 12 squared. So now let's go ahead and set an expression for d. And we're going to use this, we're going to expand this binomial here. So we're going to have the square root of 28 squared is 784 plus 30 squared, which is 900, minus 60x plus x squared plus the square root of x squared plus 144. So this simplifies to 900 plus 784 is 1684. So we have x squared minus 60x plus 1684, and we take the square root of that, plus the square root of x squared plus 144. So now we're going to have to differentiate this, and I suspect it's going to take some space. So 1/2 times the inner function to the negative 1/2. That's the derivative of the outer times the derivative of the inner, which is 2x minus 60, plus the derivative of this piece. So that's 1/2 times the inner times the derivative of the inner. So let's go ahead and start our simplification process. Here we have a 2 in the denominator and a 2 factor in each one of these terms, so I can get rid of that. So we're going to have an x minus 30 all over this term here, which is x squared minus 60x plus 1684 to the 1/2 plus, and here we have a common 2, so this is x over x squared plus 144 to the 1/2. So since we're going to be looking for critical numbers, let's go ahead and set this equal to 0, and we're going to move this to the other side. So what we'll have is, since this is going to go negative, we'll just multiply this numerator by -1, and we'll have 30 minus x over x squared minus 60x plus 1684 to the 1/2 equals x over x squared plus 144 to the 1/2. So continuing on, basic algebraic technique, we're going to multiply both sides by the denominators of each side. So we're going to multiply both sides by this denominator, so we have 30 minus x times x squared plus 144 to the 1/2. Multiply both sides by this denominator, x times x squared minus 60x plus 1684 to the 1/2. Now, I need to get rid of these square roots, so we're just going to square both sides. Now we're going to have to be cautious, because every time we square both sides of an equation, we generate the possibility of an extraneous solution. So we're going to have to check that at the end. So squaring this side, we get 30 minus x squared. The square root of anything squared is that thing, so this is just x squared plus 144. And the square root of this is x squared, and the square root of this squared is x squared minus 60x plus 1684. I sense this left side's about to get ugly, so let's go ahead and expand this binomial. We have 900 minus 60x plus x squared times x squared plus 144 equals, let's multiply through here. We have x to the 4th minus 60x to the 3rd plus 1684x squared. Now let's go ahead and multiply out this left side here. So we have 900 times x squared, which is 900 x squared. 900 times 144 is 129,600 minus 60 times x squared is 60x to the 3rd, and negative 60 times 144 is negative 8640x. X squared times x squared is plus x to the 4th. X squared times 144 is 144 x squared. And rewrite the right side. So we have x to the 4th minus 60x to the 3rd plus 1684x squared. Okay, so the x squareds cancel out. I'm sorry, the x to the 4ths cancel out. The negative 60x to the 3rds cancel out. And we can combine our remaining terms. So 1684 minus 900 minus 144 is 640. So we have 640x squared minus, that's actually going to come onto this side, so it's a plus 8640x, and minus 129,600 equals 0. So I just moved everything to the right hand side and then swapped sides. So we can factor out 320 out of each one of these terms, and we'll have 320. That gives us 2x squared plus 27x minus 405 equals 0. So I'm not going to bother factoring this. I'm just going to go straight to the quadratic formula. So negative b plus or minus the square root of b squared minus 4 times 2 times negative 405 all over 2a, which is 4. So this gives us negative 27 plus or minus the square root of 3969 all over 4, which is negative 27 plus or minus 63 over 4, which gives us two factors, 9 and negative 22.5. So obviously the negative 22.5 isn't a factor because we can't have a negative length. So our length is 9. So if we go back to our expression, we can say that the stake should be placed 9 feet from the right post, or the 12-foot post. So this distance from here to here is going to be 9. And that's optimization. So let's go ahead and move on to the next section.